Okay, hello. My name is Tallgren. I work at Nokia Networks, and my topic is about how to optimize OpenStack for NFV. So, what Nokia does is Nokia produces the so-called network elements, which are now called virtualized network functions. And what we are doing is the kind of shift that is now happening is that we are moving from sort of physical deployments to cloud deployments. So, but the shift doesn't happen overnight, so it's sort of we still have the network elements are still running on the physical hardware, but they also need to run on the cloud. So that sort of gives some limitations on sort of what kind of tuning can be done for the network elements, and it also means that to get the network elements to run optimally on OpenStack requires some tuning. So what the presentation is about is sort of some of the things that I have learned in sort of trying to optimize the performance of the network, of some of the network elements on OpenStack. So we have been using OpenStack for quite a long time now and sort of working with the network elements, and now what we are getting to this stage where we try to sort of optimize the performance and trying to get as much performance out of the deployment as possible. And especially the networking is the bottleneck, and since the kind of applications that we have are mainly using small packets, and sort of the networking performance is the key performance indicator. And what we want to have is to use this standard OpenStack networking with OVS and with sort of no special tunings, no SRIV or anything like that. And I have a number of things. I start with the easy one, and then I move to the more difficult ones, and then I actually present something that is not working with OpenStack currently. So the first thing, the easiest thing, is the security groups. So I have here on the top is the standard networking architecture from OpenStack. And what you have is that all the packets that come from a VM, they go to Linux bridge, they go to OVS, and then they go to the physical device. So going through the Linux bridge will not speed things up, it can only slow things down. So, but if you turn off the security groups, then the Linux bridges are not created and the packets will not go through the Linux bridge. So that will improve performance and latency especially. Another second thing is that with this QEMU deployment, we're using standard tap interfaces, and the tap interfaces are visible in the sysfs as just normal, like any other interfaces. So especially you can look at the queue length for the tap devices, and the default value for the queue length is 500. And that's a very small number for small packets, which means that when you're running high traffic with the standard OVS deployment and with tap interfaces, then it means that packets are going to be lost. So it's better to make it a bigger number. So that's the trick number 2. And then the third thing that can be done is this sort of CPU pinning and so forth. And that's something that was missing from OpenStack a while ago, but now things are getting better. It's supported in Kilo. And what it does is actually tells the Linux scheduler not to move the VMs around. So if you have a virtual machine doing packet processing, and then the Linux scheduler somehow decides to move that virtual machine to somewhere else, it means that some packets are going to be lost, or at least packets are going to be delayed. So that's one set of tricks. And then there's this other topics around that area, like huge pages, taking into account the PCI topology, sort of figuring out what is the CPU socket where the network interface is connected to, and so forth. And then one final thing that is sort of missing from OpenStack is this MultiQ Virtual. So what I have in this picture here is a number of virtual cores now running in a virtual machine. So the blue box is a virtual machine, and there's a number of virtual cores, core 1, core 2, and so forth. With the Virtual interface, currently it doesn't support MultiQ, so it only has sort of a single interrupt, and the single interrupt can only go to a single core, and that means that that single core will be overloaded. And you can see that this is the picture shows one view, but if you can look inside of the virtual machine, and you can look at the CPU loads of the different virtual CPUs, and you can see that one of the CPUs is getting overloaded. One thing that can be done is this trick called receive side scaling, or RSS, and that can be done sort of inside of the VM. And what that means is that when an interrupt comes in, the physical interrupt will go to a single core, but then the actual packet processing will be distributed to all of the cores. Unfortunately, what happens with the virtual machine is that although the RSS works very well on the physical deployments, and it helps sort of reducing the load on a single core, it doesn't work so well in the virtual machine, because then then you have a number of virtual CPUs which are all participating in the packet processing, and all of those virtual CPUs, they need to have access to the single to the same packet, and there seems to be some overhead which means that the system is not performing very well. So what we really need to have is to have the MultiQ VirtIO interface supported in OpenStack. It's already supported in QEMU, and there's a blueprint about the MultiQ VirtIO in OpenStack. That's all. That was the end of my presentation. Thank you.